Alright, so we've seen that in three-phase circuit, there are two basic configurations that we can have. We can either have the star, right, which is this, or we can have the delta, right? And then we've said that, and then we are saying that this configuration can be either for the load, the supply system, or the load system, right? But here, let's focus on the load system, right? Yeah. So let's see. And one thing we've said is that so far what we'll be doing here is that something we call balance. So we are starting with the balance. So what that means is that because you're talking about load, means that we know the basic equation that we've been talking about so far is V is equal to IZ, right? And this Z here is a load, and the VI voltage and current, right? Yeah. So the Z is the load because we have other elements preventing the flow of the current, right? So that will mean that we are not having only resistor. We could have a resistor, what's the name? Resistor, capacitance, or inductance. So combination of any of these two, right? All of them, right? Yeah. So that's why we have this here, right? And we are saying that whenever we have a system that is balanced, what we are saying is that it means the impedance, right, from the impedance of the loads, right? So let's say in this case the loads will be what we have here. The impedance in the loads are the same, and if they are the same, right, that will mean that the current flowing through each and every phase, right, the voltage flowing through each and every phase, and then the phase angles too are the same, right? So that will mean that uh the voltage across them will be the same, right? So that will mean that the voltage across each phase will be the same, right? And then the voltage across each phase is the same, the current across each phase is the same, and then there will be the same angle out of phase to each other, right? That's the 120 degrees that we talked about, right? Okay, so that's what we say balanced, that a three-phase system is balanced, right? That means that loads have the same impedance and therefore the same current flows through them in each phase, and then there's the same voltage flows through them, right? And the phase angles are 180 degrees apart, right? Yeah. Okay. So that's for balance, and then we are saying that what we are doing right now is just for balance, right? Okay. So let's see. So when it comes to these ones, we say we have star and delta, right? And then because of how it's arranged here, generally we say this will be the reference, right? But it can change, right? So that will mean that you can have something of this sort, something of this sort, right? So far as there's one of them that you can use as a reference, right? It's still the same thing, right? So it's still the same thing. Okay, yeah. And then when we're doing AC, we said that there are various ways for us to represent these phases, right? Yeah, these phases. And then we said, so if this one is the reference, that will mean that the phase angle is 0, right? So because we are doing a voltage now, we can write something like, let's say V is equal to, let's say if this is A and this is B, this is C. So this VA will be, let's use a similar color. Let's see. So this VA, right? This VA here, yeah, the voltage in that particular phase will be just a volt, like the voltage, like the magnitude of it, and the phase angle will be what? 0, right? Because it's the reference, right? So if it were to be the case where we have the reference one to be the vertical one, still the same thing, right? Yeah. So that will be this. So if this is, let's see. So it could be the same thing. If this is VA, then that will be, we have the voltage and the phase angle, right? Still the same thing, right? So that's what we are saying. And then when it comes to the reading of the phase angles, anti-clockwise is positive, right? So if we are trying to represent all the voltages here appropriately, this is how it to be. So let's see. So this is A, this is B. So then this B here, right? Voltage B here will be the magnitude, right? And then anti-clockwise is positive, right? So that will be phase angle, and then we have 120 degrees, right? And then this one right here will be the negative, right? So this to here is 120. When we are reading clockwise, that's negative, right? So this here will be VC, and then we have the magnitude, and then we have the phase angle to be minus 120 degrees, right? And this is not the only way of representing it, and we've seen that one way to represent these voltages, right, is when we write it this way. When we do something like this, so for VC, for instance, we can write the peak voltage, right, for that particular system, right? And then we have the sign, right? Let me make it small. So this is what we've seen. So we have VC, and we have the peak, right? And then we have sine, and we have the angular frequency time plus, and then the phase angle. This minus, right? So referencing to the reference like this one here. So that's minus 120 degrees, right? So these two here are just the same way, different ways of writing the same thing, right? And we've seen this already. Right? Yeah. Okay. But then there's one thing that happens whenever we are having these configurations. We want to do something we call line or phase quantities, right? So let's see. Okay, so let's take this. All right. And what happens is that when we see a phase, we are just, so let's say voltage, for instance. When we see a phase voltage, we are just seeing that the voltage just across that phase alone, right? So we'll see that what's happening. Okay, so when we say voltage, for instance, phase voltage, when we talk about a phase, we're just seeing what's happening along any of these ones. That's just a phase, right? Phase, whether current or voltage, right? But when we say line, it means that from the end of one of the phases to the other end of the other phase, right? So let's make an example. So let's use a delta, for instance. So let's say if we see a phase voltage, right? So that would mean that the voltage across this particular red line phase here, right? So we are taking the voltage here, and when we say line, that would mean that from the end of one phase to the other end, right? So let's see, and that one is this way. That would mean that we are checking. So this is the reference from this line here. So then the phase voltage will be like this, and usually say that it's drawn anti-clockwise, right? Because that's a positive direction, right? Yeah. So one line here, this one here, references. So from here to here is the phase, right? So now let's look at this. So now we've seen that the basic equation here, we're just going over it once more, is V is equal to IZ, right? And we're talking about the resistance already, right? So let's see. When it comes to the delta, the star and delta have slight differences, right? When it comes to the delta, let's look at the voltages first because of how it's arranged. V is equal to IZ, right? So now we are talking about V, right? When it comes to the delta, the the phase voltage and the line voltage have a relationship, right? So that would mean that if we look at, try to measure the voltage across this one here, right? So if the voltage here, so let's say V, let's make it 8, right? The voltage here, that mean that the voltage across the side, if we measure it, right, and we measure the line voltage, we've seen that the line voltage is from the end of one phase to the other. So that'll be from like something like this. Let's see. So that'll be something like this, right? Yeah. So this is the phase voltage, the line voltage, right? So let's make it VL. So you see that if we put a voltmeter here, measure the voltage, connect it here, measure the voltage, and then we measure the voltage across here, they'll be the same, right? So for the delta, the line voltage, right, is the same as the phase voltage, right? Yeah. Now let's look at the current. So now we are done with the voltage, right, for the delta side. So let's see. Minutes. Okay. So now we are done with the voltage. Now let's look at the currents. So let's say for the same delta configuration, right? So let's see. Same delta. Now I'm trying to check what happens with the current, right? Let's see. So now that will mean that we have windings. Let's see, the current will be something like this. So the whole setup will have a kind of like current flowing through it like this, right? The load, right? So they are moving in a particular direction, right? So let's see, this way, right? So that will mean that these are the line currents, right? So this will be, let's see, the current in this side, let's say red, the current in this side, let's say yellow, and the current in this side, let's say blue, right? So if we are checking the current, so these ones, the ones we've written here are basically the phase currents. But if you are checking the line current to be something like oh this. So let's say there will be one here. Let's see. Let's move this one. So this one from here, there'll be one here, right? And then from here, the red one will be one here, right? and then from this yellow as well there'll be one here. And these were actual terms, they are not just concept, they are used in a lot of systems, right? And then generally the delta is used a lot, right, because it produces more higher output, and then we'll see the relationship later, right? Okay, let's see. Right, so looking at these ones, we know these let's see. So the ones that we've just drawn out are the line current, and the ones on the phases are the phase current, right? So looking at this very well, we can use what's the name? There was a name for this particular principle. The term for that is Kirchhoff, right? Kirchhoff's law, right? So if we consider just one point here, for instance, so let's see. If you're considering one point here, the quantities involved will be this, this, and then this, right? So looking at this, it's very the ones entering, right? The ones entering will be this, the line current, this one here, and then this, right? So it shows clearly that if you are trying to find the line current, still we are on the delta, right? If you are trying to find the line current, right? So let's see, the line, right? That will be the line current will be equal to the current IR, right? Just a minute. The ones entering, the ones leaving are this and this, right? Yeah. So let's see. So that will mean that the one entering. So if you are trying to find the line current, right? The line current will be equal to the one entering, right? What current IB minus the current IR, right? And then we know clearly that these are vectors. We've already said this already, right? So if you actually go through the pain or the put in the effort to actually do the computation, you get to know that the relationship between the line and the phase current for delta is that we have the line current to be equal to root 3 of the phase current, right? Because we already know that these ones, their magnitude are the same, right? Because here we're talking about balance system, right? So yeah, the magnitude are the same. So if you actually go through the whole computation, you actually get to see that it's so, right? So you can even use the calculator to actually check the whole thing, right? There's a whole way of going through it to check it, right? So that is it for the the delta side, right? But when it comes to the star, even if you don't actually go through the whole thing of understanding it, there's a simple way for you to remember it all, right? Because we know that the whole thing that we've been doing so far is based on this equation. What we have V is equal to IZ, right? Which we got from V is equal to I, right? So let's see. So if you look at for the delta side, the voltages in the line and the phases are the same, right? But when it comes to the star, it's not so. To have the a similar relationship to that of the what do you call it? The what's the name? The current one in the delta, right? So let's see. So when it comes to the star, we have the voltage this way. So we have the line voltage. So let's use something different. So we have the line voltage being equal to root 3. Oh, being equal to root 3 of the phase voltage, right? So you see, it's not the same as that in the delta, right? And then when it comes to the current, the line current in star, right, we have it to be having a similar relationship to that of the voltage, right, in the delta. Right? So let's see, that will be, let's see, so that'll be I, right, L being equal to V, sorry, that should be I being equal to I P. And we can look at that, right? So let's see. So we know each of these ones is a phase, right? So let's see. If we want to check let's see what happens with the current, right? So let's see if we are checking the current to actually be here, right, in the phase, right? But if it flows out as this, so if this is the line current and this is the phase current, it makes sense that they are the same, right? So this is the line current, sorry, this is phase current, and the one outside. So let's do it this way like this way, this way, the same direction, right? So this one here will basically be the line current, right? So this is basically, this is also the phase current, right? And the one that moves out will be the line current. So you see that they are the same, right? But when it comes to the phase, when it comes to the voltage, it's not the same, right? So let's go about that and see. The most important thing as of right now, or this particular course, is that you'll be able to just see the relationship and get the equation. But if you want to derive to know why is that way, to find. So let's see. For the voltages, right? We know the phase voltage will be just here, right? We know the phase voltage will be just here, right? But when it comes to the line voltage, it is from one end to the another end, right? So this way, right? So that will be from here to here. In fact, let's use let's see, minute. Okay. Let's bring it here. Okay, minute. Okay, so that will mean that when it comes to the voltage, right? We know that this has a phase voltage, but when we want to check the line voltage, that, as we said, is from the end of one phase to the end of the other phase, another phase, right? So that we have a reference here, so this way, right? Another one here, and we said we do it anti-clockwise, right? So that will be this way, right? So this here is basically the line voltage, right? And we know the phase voltage is here, another one is here, right? And then when you actually do the whole computation, you get to see that yes, it is so, right? Yeah. So this is basically the relationship between these two when it comes to the current and voltage, right? Okay. And then you remember we actually said that these configurations can be done for the supply and then the load as well, right? So this is star, and what we have here is delta, right? Yeah. Star and delta. The relationship between the line and phase current, line and phase voltage and current, right? And we said that these configurations can be done for either the load or the load or the, what's the name, the load or the supply system, right? Yeah. Okay. So there are times where the load system that are attached to the supply are parallel, right? And if they are parallel and they are not having the same configuration, then you have to convert from one to another. So let's see. So system that has the load system, like multiple load systems, suppose, let's say, parallel, right? But then their configurations are different, then you have to convert from one to another. And what we are doing here so far, we'll work examples to see how what we are seeing actually makes sense, right? But here we're just trying to understand the concept as much as possible, right? So let's see. Okay. So let's say we have two load systems that are parallel, but then their systems are their configurations are different. That would mean that we can't effectively connect them, right? So let's see if you're trying to connect these two. Let's say we can connect this, right? Somehow, let's say we can connect this and then we can connect this. But what happened to this end here, right? We can't directly connect them, right? So that's why when you have a system that these two are parallel, you have to convert them to the same, right? And then that brings us to a relationship that we discussed this already, but I'm just going to look at it again, right? And here, because we are talking about balance system, we're just going to use this example to work them out, right? So let's see. Minutes. Uh, it's not working out, but we are trying to make it as close as possible. It's not working. Okay, but let's use this, right? Let's use this. Fine. So you see that somehow we've kind of find a way to stack the star within the delta, right? And there's actually a relationship for it. And when we have in a balance system, so let's consider all these to be loads. So there's a load, load, and then there's a need for us to convert from one to the other. So clearly, somehow you can see that the delta, right? The delta configuration, because it's out, just keep this relationship in mind. Because it's out, is bigger than that of the star, right? So if you have a system where it's balanced, right, and you're trying to change from, let's say, delta to star, star to delta, just keep this in mind that we have the delta being bigger than the star, right? Being bigger than the star, right? Yeah. And then if it is so, let's say you have a delta, you're converted to star, and let's say the loads are balanced. So if let's say this is a resistor, and this resistor here is, let's say 3 ohms, right? And then you are changing, yeah, this one too is 3 ohms as well, and then this one too is 3 ohms. You are trying to change the whole system to a star, right? We've already seen that the delta is bigger than the star. The relationship here is that this one is 3 times bigger, right? So it's just that, let's write it this way: delta is equal to 3 times of star, right? So if you are changing this resistance on the delta here, right, to that of a star, you just divide by 3, right? So that will mean that if here the resistance on each face is 3, then the resistance on each face on the star will be 1 ohm for each, right? So that will mean that we have 1 ohm each here, right? So that will mean that each of these ones will be 1 ohm. So that will be 1 ohm. I've already seen the relationship for this, right? So the 1 ohm here, 1 ohm on this phase, and 1 ohm on this phase, right? So basically, the delta for a balanced, right, for a balanced load 3-phase system, right? That's what we are saying. Yeah, for balance, the delta is kind of like, for each phase is 3 times that of the star. Yeah, when it, yeah, and when it even comes to the power, it's still a similar case, right? And we'll find ways and means. In the examples that we saw, we'll see similar scenarios. Yeah. So that's it for now. All right.